video is a complete in-depth breakdown of Swift reference and value types. We talk about the importance of considering what's allocated on the stack versus the heap. We also talk about copyable and non-copyable types. All information is validated by Apple reference material. All references are in the description below and are from Apple documentation and Apple session videos. We must understand the stack and the heap before we can fully understand reference and value types.
An app launches with its own virtual memory address. Within that virtual memory is your stack and heap, along with your app executable, libraries, resources, etc. We'll only be focusing on the stack and heap portions of this chart.
Let's start with the heap. Heap allocations are expensive. When memory is allocated on the heap, there's a reference that points to that memory allocated on the heap, and that reference is stored on the stack. Stack allocations are inexpensive, so it's preferable to avoid heap allocations whenever possible. Value types typically only require memory to be allocated on the stack. There's some exceptions to this that we will discuss later.
Examples of value types are structs, enums, and strings. Value types when referenced produce a separate but identical copy of that memory on the stack. This is known as value semantics.
Let's talk about reference types.
Examples of reference types are classes, actors, and closures. Reference types require a heap allocation. When reference types are assigned to a variable, it is the reference itself that is copied. This is known as reference semantics. Let's quickly compare reference and value types. So if I create a class called demo, I also want to create a demo2 variable and assign the first demo variable to demo2. Then I want to create a test string variable inside of the demo class. If I take test2 and I assign it to the new value 2, you see that this now has a value of 2 where it was previously a value of 1. That's because when you assign demo to demo2, it's just copying the reference and not the actual object. So demo1 and demo2 both reference the same object in memory. Now if we then compare this to a value type, so I'll just switch this class to a struct. I'll make this mutable so I can change the test string to 2. Here, you'll notice that the output for that first demo object is 1. And that's because when I assign demo to the demo2 variable, this then makes a copy of that demo object in memory, and I can uniquely assign different values to the test string variable. So this is value semantics.
There are a few instances where value types can incur heap allocation overhead, thus leading to a more expensive outcome than may be expected.
The first example of this is with strings. While strings and characters within a string are structs and have value semantics, characters contained within a string are still allocated on the heap. A value type alternative to a string should be used if possible. One example of a string alternative type is the UUID value type. UUID is a fixed 128 bits of memory that is only allocated on the stack. This should be used as an identifier for an object instead of a string to avoid the heap allocation. An enum can also be used as replacement for a string when setting types. You can even create an enum with a raw string representable that does not require a heap allocation.
One more example of when a value type can incur heap allocation overhead is with protocols. When a value type conforms to a protocol and that protocol is used to identify that value type, the value type must remain under a certain memory size to not incur heap allocation overhead. This is where the existential container comes into play. The existential container can only allocate 3 words, a word being a unit of data, before it has to create a reference and allocate that data on the heap. The existential container also holds references to the value witness table and the protocol witness table. The takeaway from all this is it can never be assumed that value types will never incur any heap allocation overhead. You must know all scenarios where you'll have a heap allocation and understand all the trade-offs.
Let's talk about copyable. Both class and struct conform to the copyable protocol. In fact, most types in Swift conform to the copyable protocol by default, including the any type. As of Swift 5.9, the copyable protocol can be suppressed by the tilde, allowing for non-copyable types. Swift 6 also allows for non-copyable types for generics. If you look at this example, I'm setting the demo variable to the demo struct, and then I am assigning this demo variable to the demo2 variable. What happens is when I assign the demo variable to the demo2 variable, demo2 consumes the demo variable, allows the consume behavior by default, but you can also explicitly mark it as consumed. So what happens is the demo variable becomes uninstantiated. So if I try to access the demo variable, I get an error that says demo used after consume.
To take a deeper dive into reference types, value types, and app memory and all other related topics, take a look at the description and look at the references from Apple documentation and Apple session videos. Good luck.